So let's look at during a rainy day. For relative motion, usually we have three parties involved. In this case, we choose rain, we choose ground, and we choose another one is car. What's going to happen is we have a car, for example. And the rain drops like that. If there's no wind, the rain will drop with respect to ground just vertically because Earth's gravity makes it straight, but there's no wind. This is V rain to the ground, vertically down. If you're inside a car, look at the rain will be straight. This is no wind condition, okay? No wind. Now, however, even there's no wind, but if the car starts to move this way, this is a V car to the ground. Can you imagine if you drive your car, then you look at the window, and what does the rain look like? The rain will not be straight down, it will be tilted. If you look at, if this is the window, if the car moved to the right and you are inside, if you look at it, the rain looks like that way, right? The faster you drive, the smaller the angle theta will be. The rain will tilt it more towards the horizontal. What does it happen? When you look at the rain through this window, actually you take the window as reference, like a painting frame. So this window is part of car. So what you see actually is V rain with respect to car. You look at the rain, you take the window as reference. So that is V rain to the car. V rain, I should say V rain to the car. V rain to the car is V rain to the ground plus V ground to V rain to the car. Is it okay? I should say V rain to the car is V rain to the ground plus V ground to the car. How do we get that? Remember three party, rain, ground, car? Rain is first one. Rain is first one. Car is last one. Car is last one. The third party is in the middle. So rain to the car is rain to the ground plus ground to the car. So this is a vector sum. Let's take a look. Rain to the ground is this guy. Car to the ground is to the right. Then ground to the car is this way. V ground to the car is opposite. What does that mean? If you're inside a car, let's say car drives smoothly to the right. If you look at the ground, don't you feel the ground move backwards, which is to the left? That is V ground to the car. So now we propose we need to add what? Rain to the ground, which is this one, through ground to the car, which is that one. How do you add two vectors graphically? We know how to do that, right? So we just need to put, say, tail to tail together. So this is V rain to the ground, tail. The other one is V ground to the car, tail. And once you put tail together, because we're going to add these two vectors graphically, isn't that true? You do a parallelogram, the diagonal is the resultant. Who's the resultant? That is V rain to the car. That's why when you look through the window, the rain looks like that. This angle theta, we can do a tangent theta. Tangent theta is this one, which is V rain to the ground, divided by V ground to the car, which is that. Isn't that true when you travel faster? If this is bigger, V car to the ground, bigger means longer. If V car to the ground is longer, then V ground to the car is also longer, but the opposite direction. V ground to the car will be longer because longer means travel faster. So imagine now your ground to the car is this long. This is V ground to the car. Now, how do you construct a parallelogram? This parallelogram will be this. Your diagonal now will be that. Isn't that true? Now the angle gets smaller. The faster you travel, the car to the ground, the longer the vector size, then the ground to the cars also get longer. That get longer. This part remain constant. Don't you think that angle theta will get smaller? That's why you travel faster, and you will see the angle smaller. Let's look at another example. Crossing a river. This is a river, and one side is riverbank A, the other side is riverbank B. If we have a boat, now when we buy a boat from a manufacturer, the maximum speed of the boat usually is actually with respect to still water. So I think that makes sense, because if the boat sails against the current or with the current or with an angle with respect to current, it will all cause different situations. So the manufacturer has to assume that water is still, so the boat sails in a swimming pool. So that is V boat to the water. Say this is current. A current is the velocity of water with respect to the ground. Now if we want to cross a river of certain width, let's say D, if we want to start from A and directly land it at point B, and AB line is perpendicular to the bank, which way shall we sail our boat? Now the situation is apparent that if we aim the boat, V boat to the water this way, at any time the water, which is V water to the ground, will push the boat down the stream. So as a resultant, the boat will end up a direction other than directly from A goes to B. And that is V boat with respect to the ground. Because we learned that V boat to the ground is boat to the water plus water to the ground. This is the equation for relative motion, that boat is first, ground is last, and water is in the middle. So now if we want our resultant to be along the AB line, and I think the way to sail should be this way. This should be V boat to the water, and then water pushes it. That is V water to the ground. So we can have our resultant, which is diagonal, as a V boat to the ground. So by knowing so, and we can use this strategy to figure out this angle alpha, and tangent alpha equals to this divided by that. And actually we should use sine, because since the hypotenuse is V boat to the water, so let's use sine. Sine alpha is side opposite, which is V, which is this guy, V water to the ground, divided by the hypotenuse, which is V boat to the water. We know both of them. So we can find the angle that the boat should sail. Eventually, the boat will cross the river from A, directly land on B. Now, if we have another requirement, say we don't care where we land across the river, but we want to cross the river in the shortest amount of time, which way shall we sail? And then in this case, think about this. We want to cross a distance D in the shortest amount of time. Then we should gear our maximum speed at this direction. And therefore, we should put our V boat to the water simply this way, because this is the maximum speed that we can output. Therefore, T minimum equals to D divided by V boat to the water. If we aim our V boat to the water at any direction other than this same direction as D, then the
velocity component which helps the boat across the river will be that v boat to the water times a cosine of angle theta. It is less than v boat to the water itself. So we always get less speed if we aim our boat any other direction than this direction followed distance d. So this is the best strategy. Now, by doing so, we will land somewhere else. Let's take a look. Because we are aiming the boat at v boat to the water this way, and at the same time that v of water to the ground will carry us down the stream. So as a matter of fact, when the time we cross the river with distance d, the time is this much, and how much down the stream, the x direction, which is, let's say, this way, and how much down the stream is the speed of the water to the ground times the time that we spend to cross the river. So that is v water to the ground times that minimum time. That is this. So x is how many meters down the stream that the water will carry the boat down. That is v water to the ground times the minimum time across the river. Let's look at another example. That what if we fly an airplane? Well, we start from a destination, which is, say, right here. And this is the, I should say, departure point. And the city that we want to reach is distance d due east. So if there's no wind, that is very obvious that we should fly our airplane this way. Well, when we get in an airplane, the maximum speed again is v plane to the air. Assume air does not move. The airplane flies with respect to still air. Now, as a matter of fact, there's always wind blowing towards some direction with a certain speed. So what happens is we have to first identify the direction of the wind blowing. For example, if we have this as v, air to the ground, that is wind, and at alpha degree south of east. Now, which way shall we fly our airplane that eventually we will end up east? So I think we should fly this way, which is v plane to the air of beta degree north of east. So combining that v of plane to the air plus v air to the ground, what we end is v plane to the ground. V plane to the ground is the diagonal of these two vectors, and we can end up at east. So the question is, what is the angle beta? Now, we can apply this equation towards x direction and y direction. X direction is the west-east direction, and the y direction is this north-south direction. Because this is a vector equation of two-dimensional, it has I turn and j turn. So if three vectors, two add each other equal to the third one, then this two summation of I turn should equal to this one's I turn, which means v plane to the air of x plus v air to the ground of x must equal to v plane to the ground of x. Okay, so let's take a look. Plane to the air x. Plane to the air x obviously is towards east, but it has to time cosine beta. So v plane to the air cosine beta, that is the x component. And v air to the ground x. Air to the ground x is also east. So v air to the ground east times a cosine of alpha. That gives us a v plane to the ground. And plane to the ground only has x component. So that is the plane to the ground. Now, if we can figure out this beta, because we know the speed of plane to the air and air to the ground and angle alpha, and then we can figure out what is the speed of plane to the ground towards east, then we know how long does it take to reach our destination city. That is the distance d divided by v plane to the ground, which is east. So we're going to apply our equation of this one to the y. So this is a y and a y and a y. Let's take a look what happened. Now v plane to the air y, plane to the air y is plane to the air times sine beta. So it's v plane to the air sine beta. And air to the ground y, air to the ground y is towards south. So it's negative because if plane to the air of component y is north, and the south has to be negative. So it's negative v air to the ground of sine alpha. And plane to the ground has no y. That equals to 0. This is a good equation because plane to air, air to ground, speed known. Alpha is the angle the wind blows with respect to the east. And so we can solve beta from this equation. Once we solve this beta, and we can plug in here, and then we can solve what is v plane to the ground, and we can find the time takes to reach the destination. Let's look at an example, example 4, in an elevator. Say, for example, we have an elevator, and there's a ball, which we can think about this is a simple pendulum, hanging from the ceiling, okay? And assume this distance from the bottom of the ball to the floor of the elevator is distance d, and the elevator has an initial velocity VO up, and the elevator also has an acceleration a. The question is, what if at a t equals 0 moment, which the elevator has initial velocity and acceleration, we cut the string so the ball starts to drop. Question 1 is, how long does it take the ball to hit the floor of the elevator? So how do we solve this problem? Well, as a matter of fact, think about this. Initially, both the ball and the floor are with the elevator. So they both have the same initial velocity. But what happened is when the ball gets cut, the ball is under the influence of gravity. The floor will continue with an acceleration with the rest of the elevator. So the floor accelerates up, the ball accelerates down. So as a matter of fact, this relative motion will let the ball hit the floor much sooner than without the floor's acceleration. So if we can take reference, say take floor as reference. If we take floor as reference, the v ball to the floor initial equal to 0 because both have the same initial velocity, so relative velocity is 0. The distance between the ball and floor is d. And the distance is going to, as a matter of fact, be covered by the constant accelerated motion of 1/2 of A effective t squared. This A effective actually is the acceleration of ball with respect to the floor, because that distance is with ball with respect to floor. So acceleration ball to the floor is acceleration ball to the ground plus acceleration ground to the floor. We can always do that through the third party. This is A, this is A, this is B, this is B, and this is third party. So if we choose down as positive, for example, then ball to the ground is the acceleration down, it's G. Now, ground to the floor, floor to the ground, A floor to the ground is up, then A ground to the floor is moving down with A. Because if ground to the floor means if floor does not move and the ground must move away from it. It's moving down. So moving down is positive. That is plus A. So the relative acceleration between the ball and the floor is G plus A. That is the A effective. So if we plug in that here as G plus A, and we know the relative distance the ball with respect to floor, we can solve the time it takes the ball to hit the floor. So by taking the floor as reference, it's much easier to solve this problem.